Hi guys, welcome to the Tetrahedron chemistry classes. So in today's class, I will continue from the position where I left in the last lecture. So in the last lecture, I have explained to you the working of the electrochemical cells. Now I will see how we can solve some of the problem given in the electrochemistry. So this is your first question. Write the cell notation of the following reaction. So to write the cell notation for this reaction, you have to write the two half reactions, right? So how I can write the reactions for this one? So you can focus on this particular question. So you know there is oxidation half reaction in the electrochemical cell, and next reaction is your reduction half reaction. So in this case, you can see this tin is in the zero oxidation state, and after reacting with zinc with silver ions, it is converted into Sn2 positive. That means it is your oxidation process. So oxidation half reaction, you will write in this way. Your tin, right, lose 2 moles of electron. Of course, it would be in solid state, right, and it will convert it into Sn2 positive in aqueous. In the same way, you can write reduction half reaction. You can see silver is monopositive here. Here it is in zero oxidation state. That means this process is the reduction process. As you know, decrease in the oxidation number is reduction process. So we can write 2 of Ag positive in aqueous state, and they will consume 2 moles of electrons, and they will form 2 of silver. So these are the two half reactions, and you have to write the cell notation. So in the last class, I have explained to you how we can write the cell notation. So you can recall this. To write the cell notation, first you will write your anode half cell, then you will write your salt bridge, right, and after that you will write your cathode half reaction, right. And in the last class, I also told you this oxidation half reaction is actually occurring at anode half cell, right, and cathode at your cathode half cell, your reduction would occur, right. So this is your oxidation half cell. So in the oxidation half cell, you will write the metal first. So this I have explained in this all thing in my last lecture. So if you haven't seen my last lecture on working of electrochemical cells, so here is the link. You can go through the link and see how we can write the notation. So in this anode half cell, we will write the metal first, and this anode half cell, your metal is tin, right, and after that you will write the metal ion. After that you will write the metal ion, and you know this metal ion is Sn2 positive, in this case aqueous. Since a concentration is not mentioned here, so we will not write the concentration. Then again, for salt bridge, we will write the 2 parallel lines, right, and then we will write the cathode half reaction, or cathode half cell, actually not reaction, cathode half cell. So for cathode half cell, again you will start with the metal at the cathode, that is silver is there. You will write the silver here, and then you will write the silver positive, Ag positive, and since concentration is not given, so you can write the notation in this way. If you want to write this in the proper way, so this is the Sn, this is your Sn2 positive in aqueous medium, this is your salt bridge, this is your silver, and this is your silver ion and silver again. So this is how you can write the cell notation from your if the reaction is given, you can write the cell notation. This is how you can form the cell. If you want to form a cell, electrochemical cell for this one, so this is your left hand side. Of course, this would form your anode half cell, and this will form your cathode half cell. This is how you can solve this particular one. Now moving to this one. Calculate the reduction potential. If you have given, say you have given this particular reaction, and you have given the cell, E cell, and this is your electrode potential for particular half cell, that is for the cobalt half cell. Since you know how we can calculate it, you know E cell, right, E cell, sorry, you can write what? You can mention standard here because standard is given here and standard is given here. So you will write standard here, right? So I'll come to that. What is the meaning of this standard and all? And you know, E cell equal to ER minus EL. That is E electrode potential, standard electrode potential of right hand side and standard electrode potential of the left hand side. And you know, in the right hand side, you know, that is cathode minus, in the left hand side anode is there, so you will write standard anode. So what you have given? You have given this particular value E standard cell, and this value is what? You see, this value is 1.89, so you will write 1.89 volt here. And you know, this is, if you follow the same procedure to write the reaction, you can see in this particular case, here your cerium ions positive, they are consuming actually, say it is consuming 1 electron, it is converting into cerium 3 positive. So it is the process of the reduction. So you can write reduction for this particular one, right? This is your cobalt, which is in solid state, of course, and this cobalt is actually losing 2 moles of electrons and it is forming CO2 positive. This is the process of oxidation, right? So you can also write the overall reaction for this particular one, right? But right now I am not focusing on that particular one. Because in the future or in the coming lectures I will explain the numerical based on this. But for time being, you should note down this is the reduction, this is the oxidation. So E cell is given and E cathode, that is at cathode, you know, this reduction would occur where? At cathode. As I have explained to you here, at cathode, you see here cathode half reaction, that is reduction. So at cathode always reduction occurs. So this is given for you. So you will write this particular one as such: E standard Ce4 positive by Ce3 positive minus, this minus is there, and you see anode, this is your anode. E anode is there for cobalt, you see this is your oxidation reaction. Oxidation occurs at anode. So this is given to you and this value is minus 0.28 volt. If you solve this particular one, so this would be 1.89 minus 0.28, that would be equal to E standard Ce4 positive by Ce3 positive. See this after opening the bracket, this minus minus will become positive, and this positive when come here it would become negative. If you subtract this value, that is 1.89, 0.28, that would be 1, right? That would be 6, that would be 1. So this value is actually comes out to be 1.61 volt. So this is your value actually, 1.61 volt. So this is how you can solve such kind of numericals, right? So now we'll move to the concept of the electrode potential, how we can check the electrode potential and what is the electrode potential. You'll see all these things, right? So let me check whether this area is in the frame or not. This particular one. Yeah, of course it is in the frame. No problem with that. So now I am moving to the concept of the electrode potential. So here I can write my electrode potential. Fine. So you can see This is your cell potential, and also known as the EMF, right? When no current is drawn from the cell, then EMF is equal to the cell potential. This should be important to know that. And this is the reduction potential, that is electrode potential. This is electrode potential, and this is also electrode potential. So when you take the difference of the reduction potentials of the two half cell, that is E cathode minus E anode, that will give you the cell potential. Now the question comes, E cell is fine, it is the difference between the electrode potential of the two, but what is the electrode potential actually? How we can define the electrode potential? So to define this electrode potential, I am giving you a scheme. Say this is a container, right? And in this container I am having some metal ions, say Mn positive, say Mn positive, right? That means this is metal, it is in particular oxidation state, N is the number 1, 2, 3, whatever is there, right? And in this particular one, I have dipped an electrode which is also made up of metal N, right? So it is mandatory, if you dissolve a particular metal in this cell or in this container, then your metal should be of the same metal, right? Your metal and your metal ion should be same. Now what happens, there may be a condition just like that. Say, you can think in this way, this Mn positive would be there with some negative species, not writing N, negative species. That means cation and anion is also there. So what happens, see, every metal has a tendency to undergo either reduction or the oxidation, except from some few metals like your noble metals. They generally don't react, they don't undergo oxidation and reduction. So while for other metals, it is always true that the metals would have the tendency either to gain electrons or to lose electrons. So we will consider both the situation here. Suppose it is happening like that, the metal is depositing here. Metal is depositing from the solution to the metal. That means the reaction is happening just this kind. Mn positive, they are consuming n moles of electrons and they are depositing. Fine. So what is happening actually? See, the number of the metal ions are reducing now because they are depositing on the electrode. That means positive charge is decreasing continuously. So what happens if the positive charge decreases? That means your solution would have the excess negative charge. Solution would have excess negative charge. That means you can say a positive charge is generated in the metal, right? How this situation can be simplified or can be shown in this way. Right, so say conventionally I am putting positive signs here. Positive signs here. Right, because this negative charge is increasing in the solution. That means I am saying that this metal becomes positive with respect to the solution. So you can say this situation in this way: metal electrode becomes positive with respect to the solution. You can say in this way. So what happens? This solution is also having your counter ions, that is the negatively charged ions. So here you will find the negative charges around this particular one. So you can recall this situation is what? It is forming an electrical double layer. It is forming an electrical double layer. Electrical double layer, or more correctly, this is Helmholtz double layer. Helmholtz electrical double layer rather. So whenever there is such kind of electrical double layer forms in the connection of the metal and the solution, then there would develop some potential difference. Some potential difference. And this potential difference is actually known as electrode potential. Electrode potential. So what is the definition? What is the definition here? Potential difference. Potential difference set up between metal electrode and its own ion is called electrode potential, right? And you can focus. This reaction is, what kind of reaction is this? This is actually the redox, not redox, it is a reduction process. So in the reduction, that means the oxidation number is decreasing. So for the setup of this electrode potential, this reduction reaction is responsible. So this particular reduction potential is known as, electrode potential is known as reduction potential. Reduction potential. Right. So this is how we can define this reduction potential. In the to give you the more clear idea, I am explaining this setup of the electrode potential with the help of the second example or the second situation which may be possible. Say what happens here. This is your metal electrode, right? And here in the first case, the ions were depositing on the metal electrode. In this case, you can consider in this way, the solution is having Mn positive and your X negative type of ion. Now in the another case, your Mn positive, actually this metal is undergoing oxidation, and due to this oxidation, the positive charge, that is metal ions are coming into the solution. You can write the chemical reaction in this way. Metal was in the solid state. It was removing N moles of electrons and forming Mn positive ion aqueous. In this way you can write. Fine. So these metals have ions are forming. So what happens? These electrons that would release during this particular process, they would be present here. Just in the similar way as in the previous case, the positive charge was there. So to counter these negative charge, a positive charge would surround to this particular one. Again, an electrical double layer is set up. Helmholtz double layer is set up, and when this double layer is set up, there would be a generation of electrode potential. Generation of electrode potential. Since for this potential, this electrode potential, the responsible reaction is oxidation. You can write it as oxidation. Fine. And that particular one you can write it as a reduction. So here oxidation is responsible. So this electrode potential is known as oxidation potential. Oxidation potential, right? So this oxidation potential is also the electrode potential. So this was your ER, that is reduction potential, that particular one. This is your oxidation potential, that is this particular one. But you should remember one thing, according to the latest IUPAC convention, whether the process is oxidation or reduction, it doesn't matter. IUPAC says we will always report any electrode potential in terms of the reduction potential. This is very, very important. according to the IUPAC convention, electrode potential is represented by reduction potential. And there is no difference between the oxidation potential and the reduction potential. The difference is only the sign. For example, say I am showing in this particular box, say particular metal M, it is having oxidation potential of 1.5 volt, for example. So for the same metal, your reduction potential would be negative of 1.5 volt, or vice versa. If reduction potential is positive 1.5 volt, or then this would be a negative 1.5 volt, or not only 1.5, any value which comes out for the particular metal. So what you have to do to convert oxidation potential into reduction potential, or reduction potential into oxidation potential, you have to simply change the sign. If oxidation potential is positive, then reduction potential with the same magnitude would have the negative sign, right? If your reduction potential is negative, then your oxidation potential would be positive with the same magnitude. So this is the concept of the electrode potential. Now the question comes, from where this electrode potential is actually coming. From where it is actually coming. So now I am writing the expression for this particular one. So you can check in this way. See, if I have this particular situation, so I can write for this particular one, del G, that is free energy, or the Gibbs free energy, that would be equal to del G standard plus RT ln, that is natural log to the base E, and I can write for this particular one, activity of this metal divided by activity of this metal ion, right? Or you should note down one thing for dilute solution. For dilute solution, activity can be taken as molarity, right? See, this activity is actually a different term which is not exactly equal to the molar concentration. But for dilute solutions, activity and molar concentration both are same. Otherwise, you should note down one thing, activity actually depends on fugacity. And fugacity in terms depends on diffusion rate. So this is just for your knowledge, right? And I'll go to the advanced topic of electrochemistry, then I will explain all these things. But right now you can adjust for this particular one. So what I can do, I can write this particular equation in this way. Del G is equals to del G standard plus RT ln molar concentration of M divided by molar concentration of Mn positive. As you know, what is del G actually? Del G equals to negative NFE. Del G refers to the negative NFE. This is free energy. N is the number of moles of the electrons involved in the redox reaction, right? And F is the Faraday's constant. For practical or for calculation purposes, we will take this F as 96500, and this E is actually the potential, electrode potential, right? Negative NFE. And why negative NFE? You should know these reactions which are occurring in the electrochemical cells, they are spontaneous reactions. In the last class, I have explained the things with the help of the galvanic cell, that is your zinc and the copper cell. So they are reacting reversibly, right? And they are reacting spontaneously. If the reaction is spontaneous, you should note down one particular thing. If the reaction is spontaneous, then del G is less than 0. Of course, it is negative then. That's why I am putting this del G negative NFE. So what I can do, I can write NFE here. And here again I can write NFE standard. Here is the standard. So don't confuse with the standard term. Standard means all the measurements, all the experiments were done in the standard conditions. And in standard conditions, you know the lab temperature, which is 25 degrees centigrade. And if you are doing a reaction at atmospheric pressure, then you will use the 1 atmospheric pressure. But according to the latest IUPAC convention, now the most fundamental unit is the bar. So the reactions are at 1 bar pressure and 25 degrees centigrade and with the pure substance of 1 molarity. These are the standard conditions actually. So this is what this particular one. So you can write RT, this is Ln, this is M, again you can write Mn positive for this particular one. So what you can do, you have to calculate the electrode potential, so you can write E here. And if you rearrange this particular one, right, so this is negative again, you can write negative here. So this would be negative NFE standard divided by NF plus RT by NF. So because there is positive charge, so you have to take you have to solve this particular expression by taking the LCM. So this NF would go to this one as well as to this particular one. That would be M divided by Mn positive. So this would cancel out. So what you left with actually? You left with your E equals to E standard minus RT by NF natural log M divided by Mn positive. Right? In this way you can write. You can, however, you can further simplify this particular expression. You can further simplify it. How? You see, you can write E as such. This would be your E standard minus RT NF, and you can write here 2.303, and you will convert this ln into the log, and you will write 1 upon Mn positive by M. You can write in this way. Why I am writing? So you should remember one particular thing. When you convert log to the base e to the base 10, so here if I am writing ln, that means it is the log to the base e. If I am writing log, that means understood it is to the base 10. If you convert this log base e to the base 10, that means you have to put the value of the log e and then further solve at the thumb. So if you calculate mathematically, then it will comes out to be just like this. But you should remember the thumb rule. Whenever you are converting log to the base e to the base 10, then you have to multiply the expression which is just before your log expression with this value 2.303, right? And here I am writing 1. Why I am writing 1? Because you know the contribution of this molarity can be taken as unity, because in the electrochemical cells, you know, only charged species are responsible for the flow of the current, right? That's why we can take the activity of this particular one. So this is actually the expression for the electrode potential. This is the expression for the electrode potential. That is E is equals to E standard minus RT by NF 2.303 ln RT log 1 by Mn positive. This is how you can write, and you can further simplify this particular expression. How? This is E, you can write E standard here. So this is minus, the value of R is 8.314 joule per Kelvin per mole, right? T, you will take your 25, that is 273, that is 298. So you will write 298 Kelvin here, you will write 2.303 here, and again it would be divided by the value of the F. Value of F is 96500 for calculation point of view, and this would be log 1 upon Mn positive by Mn. So the expression would come E equal to E standard minus 0.0591 by N log of 1 by Mn positive. So this could be the expression, right? So don't confuse here. Don't confuse here. I have written negative here, then I have taken this negative here. So you can write in this way. This would be negative, right? When it is gone here, then this would be negative. If I change the sign, then of course it would become in this way, right? So if it is negative, then this is also your negative, this is your positive. If you rearrange, then it would become just like this. You can go through this particular solution. This is the concept of the electrode potential. Now very quickly I am giving you the more general expression for which you can easily write the expression for any equation. See, here you can write concentration dependency of cell potential. Basically, I am going to describe now Nernst equation. So how I can write the Nernst equation? I am giving you a very general expression. Say for example, if you have species A moles of A, similarly say B moles of B, and they are reversibly reacting to form C moles of C plus D moles of D. In this way you can write it. So if you very quickly calculate the rate constant for the forward reaction, you can check in this way. Rate of the forward reaction, this would be equal to the Kf concentration of A to the power of A, concentration rate of the backward reaction which is going in the backward direction, that would be equal to Kb concentration of this C to the power of C, concentration of D to the power of D. Since there is equilibrium, so at equilibrium you can write Rf equal to Rb, and your Rf is Kf A to the power of A, B to the power of B, that is equals to Kb C to the power of C, D to the power of D. Then you can write your Kf by Kb, that would be equal to concentration of C to the power of C, concentration of D to the power of D. Remember, this concentration is the molar concentration. So this is the molar concentration of A to the power of A, and this is the molar concentration of B to the power of B. This factor is actually your Kc, and it is also known as the reaction quotient. So I can write Q equals to C to the power of C, D to the power of D, right? Then A to the power of A, then B to the power of B, right? If I want to write the expression for this particular one, this particular expression, if I want to write the electrode potential for this particular reaction, so how I can write, there is a very simple thing which I have explained, that is del G equals to del G standard. Nothing wrong with this one. plus 2 point, not 2 point actually, it is your RT ln Q. Here I am writing Q. This particular Q is given and I am writing the expression for this equation. Nernst equation I am writing for this expression. So you can write as there negative NFE, that is equal to negative NFE standard plus RT, this is ln, and ln Q is here. If you solve this particular one, that would be equal to E with negative sign, say, or say I am not going into that much of detail. I am straight away solving it because I have solved this particular expression in the previous case. So you will have your E standard in negative RT by NF ln Q. If you further put the value of the R, that is 8.314 joule per Kelvin per mole, 298, and this 96500, and converting it this log to the base e to the base 10. So you will have your final expression in this way: E equals to E standard negative 0.0591 divided by N log of, what is Q here? You see, Q is this particular one, concentration of C to the power of C, concentration of D to the power of D, divided by concentration of A to the power of A, concentration of B to the power of B. In this way you can write your Nernst equation for that particular reaction. Now if you want to calculate, if you want to know if you want to write this Nernst equation for a particular type of reaction, so now it's very easy for you to write. How? Say I am giving you this particular question in this way. Your elementary reaction, elementary redox reaction, zinc solid plus copper in aqueous medium. This was your elementary reaction, right? And it is going to zinc 2 positive and it is depositing copper solid, as I am writing it this way. Say, fine. So how I can write this reaction for this particular one? Now it's very easy. E equals to E standard negative 0.0591 divided by N log of, here you can write these species, concentration of Zn2 positive ion, because nothing is there in their stoichiometric coefficient, so no need to write the power of that particular one. Similarly here copper is there, you can write copper solid, the concentration of this particular one, divided by this as well, say Zn2 positive, and this is here, no, not Zn2 positive, it is Zn actually, this is Zn, and this is Cu2 positive. In this way you can write. Now you can recall one very important thing. I have told you these neutral metals contribution can be taken as unity, so you can write for this Cu as 1. Similarly for this Zn you can write 1. So your final expression become E cell, because they are constituting cell now. So we can write E cell, that is equal to E standard cell negative 0.0591 divided by N log of Zn2 positive divided by Cu2 positive. So this is how you can write the Nernst equation for any reaction. You can write the Nernst equation, and this is the negative sign. In some textbook you can find this expression in the reverse way, that is your copper is up and your zinc is down. but you will take care of this sign also. Then you will find this positive sign. That means if I change this sign as positive, automatically this would reverse. But if you are putting a negative sign, so this is a trick. I am giving you the trick. This is very, very important for writing the Nernst equation. If you are putting the negative sign here, then oxidized species would be in numerator. And your reduced species would be in denominator. Sorry for my handwriting. Actually, this is the problem with me, and I have also lots of comments against my handwriting. It is not very clear, but I am trying to make it clear now. So this is denominator. Right. So this is, see here you can see in this particular reaction zinc is oxidized. So it is in the numerator if you put the negative sign here. If you put the positive, then the condition would reverse. So this is the one way of writing Nernst equation. So if you have given any kind of reaction, then you can very easily write the Nernst expression for that particular one. However, there is another way of writing your Nernst equation, which is a sort of derivation type of thing. So if the length of the video is not increasing too much, so I am giving you that particular way also. Okay, it is taking 41 minutes actually till now. So we can, okay, very quickly I can write this. Please watch the video till the end, because these are the basic things and very, very important to understand the physical chemistry. So how I can write? You can think in this way, right? I can write electrode potential for Zn2 positive by Zn. So why I am writing it is as it has Zn2 positive by Zn. I am why I am not writing it as Zn2. Zn is above and Zn2 positive is down. Recall your cell potential or your electrode potential will always be shown in terms of the reduction potential. So this is actually showing the process of the reduction, that is Zn2 positive is reducing to the Zn1. Right, that's why it is right. I am writing in this way. If you write that Zn by Zn2 positive, that means you are representing the oxidation potential. There is one way, right? So this would be equal to what? See, E standard Zn2 positive by Zn, right? Here you can write negative 0.0591 divided by 2 here. The value of N would be 2 now. Why value of 2? Because two reactions, 2 moles of electrons are involved in the process. You can see in this way, zinc when loses 2 moles of electron, it is forming 2. So 2 is there, that's why I am writing 2 here. Fine. This is one way. And then of course their log 1 upon Zn2 positive. Actually it should be like that, Zn by Zn2 positive, but the contribution of Zn would be taken as the unity. So I am writing in this way. So this is the same like expression number 1. Fine. And then you can write the same thing for E copper, Cu2 positive by Cu, again in terms of the reduction potential. So this would be E standard Cu2 positive by Cu, negative 0.0591 divided by 2 log of 1 upon Cu2 positive. This is the expression number 2. You know how I can calculate the E cell? E cell I can calculate ER minus EL, that is E cathode minus E anode. You know, in this particular cell, this copper half cell is your cathode half cell. So you can write here cathode half cell, and with this you can write this anode half cell. So you can very quickly write the values ER. Your ER is actually E standard Cu2 positive by Cu, negative 0.0591 divided by 2 log of 1 by Cu2 positive, right? This is the value of this ER, and what I can do, I can put this expression in the bracket. I'm putting the negative sign here, this negative. Now I'll write for the EL. EL is this particular one. So how I can write? E standard Zn2 positive by Zn. You can write in this way. This is negative 0.0591 by 2. Again, this is log Zn2 positive by. So again, the same thing. I'm not writing properly actually, and I have received lots of negative comments about this particular one. So this happens here. So finally you will write your E cell, right? What you can do, you can write this E cathode minus E anode here. That is E standard for Cu2 positive by Cu negative. E standard Zn2 positive by Zn. You can take this as in the bracket, and your 0.059 by 2 you can take it as common. 0.0591 by 2, and then you can write your log expression. If you solve the value, solve the problem by putting that as log m minus n, that will give you log m by log m by n. In this way you can write. So here you will write again your Zn2 positive, and this is your Cu2 positive. So I have skipped a step here for this taking, but these are the pretty basic things. You can solve this by your own, and finally you can write it as, you can see, E cell equal to E standard cell. So E cell equal to E standard cell, rest all things would remain same, 0.0591 by 2 log of Zn2 positive divided by Cu2 positive. This is how you can write the Nernst expression, and from this expression it is quite clear that these all are actually temperature dependent and your concentration dependent. See, in the next class I will explain how this cell potential is varying with the variation of the temperature and the concentration. So this is how you can see the concept of the electrode potential, cell potential, and the Nernst equation and their equations, lots of things, right? So guys, that's it for today. So if you are new here, and see, if you are a regular viewer also and you haven't subscribed my channel yet, so please subscribe the Tetrahedron chemistry classes, and don't forget to press the bell icon for the latest notification. Thank you very much.